Everyone. I'm coming to you live on location today from Devil's Marble Yard. Decided I wanted to take a hike today, but brought my tablet with me. So before I get any further up, I'm going to make a video about section 4.4, which is something we've already touched on, but it's finding the general solution of systems of differential equations when we have two real eigenvalues. So I'm going to take you through the whole process. You can think of this as being an example of what we did in the last section. Alright, let me make myself small again. Alright, so first thing I want to do is convert this into a matrix form so that I can get my matrix that I'm going to be finding my eigenvalues of. If any of these steps are seeming a little strange, go back and watch the linear algebra review videos, especially the last one, part 4, and that will help you see kind of what I'm doing here. But it looks like everything's in the right place that it needs to be for me to start this problem. So this y vector is going to be y1, y2, and this y prime vector is y1 prime, y2 prime. And so I've got my system of differential equations written in this matrix and vector form. So I'm going to start finding the eigenvalues. So I'll kind of let you know what I'm doing on the side here, and I'll show all the work over on the left. And we put this into a matrix, a vector form. Okay. So we're going to find the eigenvalues of this. That means we're going to be starting with this equation, that the determinant of a minus lambda I is equal to 0. So that means that the determinant of this matrix is equal to 0. So this times this minus this times this. So we get a plus. Is equal to 0. Okay. That looks right to me. So no plus lambda term here. Oh, sorry. I corrected myself twice up here. There, that's looking a little better. Okay, so we get lambda squared, these cancel out, minus 1 is equal to 0. So it looks like lambda plus 1 times lambda minus 1 is equal to 0. So we have that lambda 1 is equal to negative 1, lambda 2 is equal to positive 1. So we found our eigenvalues. Next thing is to find our eigenvectors. And we'll start with finding first eigenvector using this first eigenvalue. I plug it into this formula here. That a minus lambda I times our eigenvalue, or eigenvector, is equal to the 0 vector. So that means that we have, let's see, what were our values here? 7, negative 3, 16, negative 7. Just double checking. Okay. 7, negative 3, 16, negative 7. Okay. But in this case, this is going to be plus 1, plus 1. Looks like this. So the augmented matrix that I'm going to be solving is going to be 8, 16, negative 3, negative 6. And that's going to be equal to 0, 0. I think I'll divide this one by 2, since it looks like it's going to be identical to this one up here. And then subtract it from the top row. What this tells me is that I've got 1 degree of freedom. And this tells me that 8x1 minus 3x2 is equal to 0. In this case, we have a choice of what we want x1 to be equal to. If we chose x1 equal to 0, then we wouldn't get something that we can use for an eigenvector, since our eigenvector would be 0, 0, based on this equation. So we chose x1 be equal to 1, since x1 can't equal 0, which I think is a good choice. So we chose x1 equals 0, and that means that 8 minus 3 x2 is equal to 0. So x2 is going to be equal to negative 8/3. These are just the values that you get when you choose x1 equal to 0. So we could say another choice might be if we multiplied both of these by 3. If we multiply both of them by 3, we get 3, -8. So we could use either one of these, but just make sure that they're scalar multiples of each other, and as long as that's true, then you should be fine. Okay, so that's the first eigenvector, second eigenvector, and I was going to be using lambda 2 is equal to 1. So this time it's -1. And I'm skipping a few steps here, but similar to what we did last time. Yep, 6. Okay, we're good. Okay, 6, -16, 3, and this one's going to be, looks like 8. I'll always try my best to give you these types of linear algebra pieces to do that you'll be able to do in a good time in the exam, that as long as you have the Gaussian elimination down, then you should be able to perform all of these. So I'm going to divide this. And then eliminate it. Oh, sorry. So we get a degree of freedom. And we get that 3 times x1 minus 8 times x2 is going to be equal to 0. So for the same reason we did last time, we're going to choose x1 to be equal to 1. And that means that 3 is equal to 8x2 based on this formula. So x2 is going to be equal to 3/8 this time. So our second eigenvector is going to be 1 and 3/8. Great. So overall, it's good to kind of summarize these so you don't have to, well, I don't have to keep looking up. Right there, my first eigenvalue is -1. First eigenvector is equal to 1, -8/3. Lambda 2 is equal to 1. There we go. Okay. So, once we've gathered everything up, we find the general solution. And for this case, where we have two unique real eigenvalues, we can write the formula like this. Our solution, y vector, is equal to c1 e to the lambda 1t times the first eigenvector plus c2 e to the lambda 2t times the second eigenvector. So let's just plug everything in. C e to the negative t times 1 negative 8/3 plus c2 e to the t times 1 3/8 vector. And as far as A is concerned, part A said to find the general solution. So I might as well label it. This is our general solution to the system. And this is a great form to have it in, right? Because you can see eigenvalues and eigenvectors all displayed right there. The second part, well, I won't scroll all the way up, but I'll just rewrite it. So the second test is basically to make sure that this solution y1 vector and this solution y2 vector, I want to see if these are a fundamental set. So to answer that question, need to find the Wronskian. For the Wronskian, in chapter 2, when we found the Wronskian, that looks like this. That looks like y1, y2, y1 prime, y2 prime. And we found the determinant of that. In chapter 4, the Wronskian is going to equal the determinant of our solution matrix. So if you need to go back and look to see what that solution matrix is, if this is the first time seeing this, go back and watch the linear algebra review videos. But for this one, it looks like we've almost got it in the form where we can look at the solution matrix. So is based on the formula that I have the general solution up here. It's going to be e to the negative t negative 8/3 e to the negative t e to the t and c2 is going to be 3/8 e to the t. This is one of those situations where it'll be good to use Abel's theorem. So Abel's theorem is the equivalent to what it was in chapter 2, where we could say that we can plug in any value of t that we want. So I'm just going to temporarily define t as 0 to make everything easier. So the determinant of this matrix evaluated at 0 is going to be the determinant of 1, 1, negative 8/3, and 3/8. If we take this determinant, this is 3/8 minus, so plus 8/3. Whatever this is, it's not 0. And again, same rules for whether or not it's 0 apply to whether or not this is a fundamental set. So we say a determinant of our solution matrix is not equal to 0. Therefore, we can say that the solution set and these are our solutions, y1 and y2, our first column and our second column here. Let's see if I can draw curlies around my face. Okay. Then the solution set is a fundamental set. Okay. So the next couple of videos are going to be doing the same thing, but we'll see what happens when you have repeated roots, or if you have roots that are complex. And by roots, I mean eigenvalues. So anyway, that mistake's just going to stay in the video since I've been talking for 20 minutes, and I've got a hike to do before the sun sets. So I'll see you in the next couple of videos, and stay safe.